Welcome to Scalable Prototyping. My name is Juan, and in this episode we are going to review a PC-based USB digital oscilloscope, the Hantek 6022BL. Working with this oscilloscope is really convenient, but there are some caveats that we should be aware of in order not to blow up our computer. The setup is quite simple. We just need to connect via USB to our computer and connect the two probes for measurements. I've labeled them so it's easier to know which one is connected to which channel. Once connected, we can now open OpenHantek to operate our oscilloscope. If properly connected, it will be automatically recognized by the software. To calibrate the probes, a 2-volt pulse train at 1 kHz is provided. We connect the alligator clip to the ground and the probe to the pulse train output. The probes can be set up for reading high voltages with a magnification slider located at the handle. If we set the position to ×10, we will have to multiply our readings ×10. Therefore, we will be attenuating our measurements voltage. That is, for a 1 voltage difference, the probe will read 0.1 voltage. This allows us to measure higher voltages, and for the calibration we want to have the maximum resolution, so we leave the slider at ×1. If we enable channel 1 in the software, we will be able to see the train pulse. We can now adjust the redraw trigger, which by default triggers on the rising edge of the signal. We can also adjust the redraw starting time. Now I activate channel 2. As we can see, the channel 2 requires some calibration, as the pulse train is not perfectly squared. The probes have 2 screws that allow to adjust and correct this effect. We adjust the screw until the waveform becomes squared. We can also select different measuring scales in the software. I will select the 1 voltage so it fits nicely on the screen. Surprisingly, the scale doesn't seem to match with the axis, but fortunately the measuring tool works perfectly. We can turn on the measuring tool for channel 1 and check that the voltage of the train pulse is indeed 2 volts at 1 kHz. We can also adjust the position of the serial reference. Holding the Alt key allows to move it with more precision. We can also choose different time resolutions. 10 milliseconds is the coarsest resolution possible, and we can get down to the nanosecond scale. Below 100 microseconds, the waveform doesn't fit the screen, and the trigger stops capturing the pulse train. We can nevertheless go down to 200 nanoseconds. At this scale, the pulse train doesn't look so squared anymore. We can record the signal using the single capture mode. We can press play until we capture the signal. We can also perform a spectral analysis for each of the channels. In this case, we can measure how the signal actually corresponds to a 1 kHz pulse train. This USB computer-based oscilloscope is very easy to use and very affordable. The downside of having it connected to our computer is that we risk to damage it. It's easy to avoid any problems if we understand the reason why. The potential problems arise from the fact that the ground alligator clip is short-circuited to the computer's ground. Depending on our computer's charger, the computer ground could also be connected to mains earth, as it happens to be with my laptop. The easiest way to figure it out is to measure it. Here we can see that there are less than 500 ohms between my computer ground and the earth mains. Connecting the alligator clip of the oscilloscope is effectively the same as connecting a 500 ohm resistor to the earth mains. If we happen to connect the clip to a source capable of providing a lot of current, all this current will flow through this virtual 500 ohm resistor and effectively burning our computer. As long as we keep this in mind, we should be fine. But if we want to play the safe side, There is no risk if we measure battery-powered devices or devices that are powered with our computer USB. So perfect for all our microcontroller prototyping. For more details on the risks and how to avoid them, I will leave a link to a fantastic video by Dave Jones where he covers with great details and diagrams the different consequences of connecting the alligator clip to the wrong place. Alright, thank you very much and see you in the next video.